This is the 8-bit shift register. This 8-bit shift register consists of 4 8274 chips, with each chip having 2 D flip-flops and the outputs being connected to LEDs, with each LED representing 1 bit. The parts used in this project are shown in the bottom right. So this project is divided into 2 parts, the D flip-flops and the 555 timer in monostable debounced mode. And the clock output is represented by this LED and will stay on for about 1 second. At the same time, the first LED will stay on, representing 1 bit. Every time I click this, the subsequent LED will turn on. And this is the data input. So if I hold on to this with the clock input, the first LED will turn off, and then it will shift on to the next LED. And this last button right here is the clear input. So it's gonna reset all the outputs back to 0. Now let's get into the nitty-gritty of this project. Here's a table showing the outputs of the shift register in binary, hexadecimal, octal, and decimal, with the highest value being 8 ones in binary, FF in hexadecimal, 377 in octal, and 255 in decimal. This is the waveform of the 555 IC in debounced monostable mode, which produces a high output for a duration before going low. Since the chips are positive edge triggered, the outputs go high on the clock's rising edge. Here is a schematic of the D flip-flop the circuit uses. Since Q is the only output being used, it can only produce a high when both data and the clock input are high. The inputs of the upper NAND gate would both be 1, producing a 0, while the lower NAND gate would have a 0 and 1, outputting a 1. Since if any of the inputs of a NAND gate are 0, the output would be 1. So Q is high, and not Q is low. Here is the D latch on the breadboard, with the left LED representing Q, and this one representing not Q. This button right here represents data, while this one is the enable / clock input. So if I click data, the output will not change. If I hold enable, still does not change. If I hold both of them, Q turns high. The D latch follows this truth table. Let's use this property of D latches to examine shift registers. So when the clock input is on its rising edge and D is high, the flip-flop D has a high output. All the other registers are still low because the data inputs are low. When the clock input is applied again, flip-flop C is high since the data, which is wired back to the Q output of flip-flop D, and the clock input is high, so 2 bits are on. We can show the shifting of bits by grounding the data input of the D flip-flop, which will make the C flip-flop still high since the clock signal is provided, and so it will latch onto its output. The next flip-flop B will also be high since the data and the clock signal are high. So the 2 bits D and C shifted to C and B when the data input of the first flip was grounded. To conclude, this project is a great way highlighting how computers store information on a foundational level.